Okay, so let's do an example to calculate both r, which is the correlation coefficient, and r squared, the coefficient of determination. So let's say we have a situation where we have this company and it measures its monthly spend on advertisement. So in this month, they spent $14,000. In this month, they spent $55,000. And they randomly sampled 5 months here for their advertising budget. And over here is the profit they got in that month. And they want to see if the advertising budget predicts profit and how strong a linear relationship that is. And in real life, you'd have way more than 5 data points here, but just to make the computation easy, we're just limiting it to 5. So in the month that they spent $14,000, they had a profit of $56,000. In the month that they spent $55,000 in advertisement, they had a profit of $71,000, etc. And we want to find if there is a linear relationship between these two variables and how strong it is. So in order to calculate the coefficient of determination and the correlation coefficient, at least the way that we learned it, you'll need the regression line. So calculate the regression equation for this data. Maybe pause the video now and give that a go. It'll be good practice. And once you've got that, unpause the video and I will write down the equation to make sure that you've got the correct equation. Okay, now that we're back, I calculated a equation of y hat equals 0.541x plus 39.06. So that's our regression equation. And now to calculate r and r squared, maybe let's build a little bit of a table here. So I'll write it a little encapsulated. I'll have our x value, we need our y value, we need our predicted y, we need our, and I'll just do it like this. I'll leave a column out. We need the difference between our actual y and our predicted y, and I'll just square it right in the table. And similarly, we need the difference between each y value and the mean of y, and again, I'll just square that in the table just to save room here in this video. And in fact, I'm going to erase this guy and give myself just a little more room because that'll involve some decimal places. So something like that. Okay, so I'm just going to copy down the x and y values here: 14, 56, 25, 40, 55, 71, 61, 73, 70, 77. Okay, and now what I'll do is I'll just calculate one row like I did for a previous example, and then I'll pause the video and fill in all the other rows, and you can do this as well and just check that you're doing it correctly. So we need our predicted y, so let's do that. It's going to be y hat equals 0.541 times 14 plus 39.06. So our line predicts that if we spend $14,000 on advertising, we are going to get a profit of $46,630. We'll round it to 2 decimal places, we'll say. $46,630,000. We'll put that in there. And now let's take the difference of those, 56 minus 46.63, and we'll square it. So that will give us our error squared. Another word for that as well is our residual. So let's go ahead and find that. And we should get, again, the 2 decimal places, 87.72. So we'll put that there. Great. Now we need the mean of y, so we can calculate that over here, the mean of y. If I add up all 5 of these values and divide by 5, I get 63.4. So that's the mean of our y values. Okay. So we just need to calculate the difference between our y and the mean y, and then just square it. So we're going to get 60, or let's do it in the correct order. So it's going to be 56 minus 63.4 squared. And if we calculate that, we get 54.76. Okay, so there are all the values for that row. Maybe pause the video now and see if you can calculate the values for the other rows as well. Okay, so we have our value here. I calculated each of the values for the table for the other rows here. And I added up all of the sums of the squares of our errors and the sums of the squares of the difference of each y value to its mean. The sum of the squares total is called, or you can call it SYY. And then we can just calculate our r squared. It's going to be 1 minus the sum of the squares errors, 251.76 over 937.2. And if we calculate that, we see that we get 0.7314. So the regression explains 73% of the variability in y depending on x. And then our r is going to be the square root of r squared, and it's going to have the same sign as the slope of our regression line, and the slope here is 0.541. So that's saying that for each extra $1,000 we spent in advertising, we expected an extra about $0.541,000, so $541 worth of profit. So our R value is indeed 0.855. So this is fairly strong. We'll call this a strong linear relationship. So that indeed is our R and our R squared, or coefficient of determination, and our correlation coefficient. A quick and important note here. So this is a very common mistake people make. They might see a high R squared value in a regression. They might think, well, it must be that X is causing Y. But that's not always true. So you can imagine, this is kind of the classic example. If we graphed two variables, ice cream sales and drowning deaths per year, it turns out that this will be, let's say, ice cream here and drowning deaths here. It turns out that as ice cream sales increase, so do drowning deaths. But obviously, it's not that ice cream sales cause drowning deaths. Of course, that's ridiculous. What's going on is, of course, it's called a confounding variable. There's no causal relationship, but there's some variable that relates both of them, and that is, of course, temperature. As temperature goes up, ice cream sales go up and drowning goes up, since people buy ice cream when the temperature is warm and people go swimming when the temperature is warm. So this relationship doesn't exist. What's really happening is that temperature is causing ice cream sales and temperature is causing drowning deaths. So that there is called a confounding variable. And just quickly, the other thing that comes up a lot is maybe it's just by chance that these two variables do have some sort of relationship. So it could also be just by chance. And probably the easiest way to see this, if you go and Google the following thing, spurious correlations, you'll find a website that shows some really fun and cool spurious correlations. It turns out that, for example, U.S. spending on space and technology is very highly correlated. Let me write that a little better. Correlated. It's very highly correlated with suicides by hanging, strangulation, and suffocation. So let's just call them hanging suicides. As one goes up, the other goes up, and at the same rate. And obviously, one is not causing the other. It's just by chance that this is happening. But I think it's worth Googling spurious correlations, visiting that website, and you can see a whole bunch of them. And sometimes it just happens by chance. So there's some two good things to note about regression.